Good morning or good afternoon, everyone. Welcome to session 16 of the Virtual Hot Water Forum this year. This session is on plumbing and modeling system design. Well, let's see. My name is Gary Klein, and I'm going to be your moderator today. Before we begin, I have a few housekeeping announcements. Your screen is customizable. Feel free to make various windows as large or as small as you would like. You can even minimize them to the drop-down menu at the bottom of your screen. Click through widgets at the bottom of the screen to be sure you are listed in the menu. Attendees are in listen-only mode but can submit questions to the Q&A box at any time through the webcast. Presenters will respond to questions throughout and at the end of the presentations. The Q&A can be accessed in the menu at the bottom of your screen if it is not already visible. All presentations will be available for on-demand viewing within a few days on the Engagement Hub. At the end of the session, we will be opening chat rooms on the Zoom platform for anyone who wishes to continue the conversation regarding the session or to ask further questions of the presentees. To access Zoom chat, there is a chat room icon in the menu bar with the link. On behalf of ACEEE, we would first like to recognize and thank our sponsors for this event. And I'm going to move to another slide so we can see the names. Ream and A.O. Smith have been longtime, big-time supporters of the conference. We thank them a great deal. Bradford White, Jackson EMC, NIA, and SoCal Gas, we also want to thank for all their support over the years. So we have 4 speakers this session, and I'm going to do all of their short, very, very short bios now, since you all can read the bios online. Hold on, I see a Q&A, and I'm worried that it's something that I have to deal with. Yes. Would all the people on the phone right now close their mics, because we're hearing background noise. One of the attendees can hear it. Thank you all very much. Thank you for pointing that out, Rick. Always good to keep us in check. All right, where did it go? I need the screen. Preview screen, attendees live view. There we go. All right, so we have 4 speakers. First in order is going to be Emily Higby with Redwood Energy, followed by Rich Houle with Reliance Worldwide Corporation, Jeff McGuire with the National Renewable Energy Lab, and then Yanda Zhang from ZYD Energy. All of these discussions are going to be talking about how we model and design plumbing systems from various perspectives, and I think you'll find it very useful. All right, with that, I think we should get started. Emily, I want to give it over to you. And there you go.
All right. All right, you should be seeing my first slide there. So I'm going to be presenting on some ongoing research that Gary and I have been doing, or Gary and Redwood Energy has been doing. And we're testing pressure drop in modern pipe and pipe fittings. So motivation, materials, and methods have changed. Our current sizing equations are based on old data, based on steel pipe, threaded, and flanged fittings. And that data was actually collected way back when in 1895. You can ask Gary and Larry Weingarten about the research in depth there. So now we have new materials and new fitting technology. Also motivation, we want to use smaller pipes, less energy, less materials costs, less water use. If you've heard Gary speak, you've heard him talk about this as well. And we're actually implementing this at some of our projects. So this is an example in Oakland, a project called Coliseum Place. We're using 3/8 inch and 3/4 inch manifold. And it's also like a distributed system. So there's one ring tank per 2 apartments, or one individual tank per 2 apartments. Also motivation, there's no existing method of test, pressure drop through fittings. This is 2 tables that you can find online when you're trying to size. For example, here looking at 5/8 inch, one says 1, equivalent length, and one says 1.5 for equivalent length. You know, just pointing out what's the source of the data. Is this the internal or outside diameter? What velocity were these tested at? So there's a lot of variation in these tables. And so this is what we came up with to test this. Some of the key design elements. There you can see the test segment, which is kind of like a coil of pipe with 10 fittings. And the total length is 16.25 feet. We have switchable test segments, so we can test from 1 inch down to 1/8 inch. And there at the bottom, we can see the flow control. So we're testing velocities from 2 to 10 feet per second. And then looking a little closer, some more design elements here. We have 2 visual pressure gauges, but also a differential pressure gauge. We have 2 temperature sensors, one in and one coming out, to see if we have constant temperature. And we also have a flow meter, make sure we're constant there as well. And then, so this is located in Arcata, California, and we have relatively steady pressure coming in from the city, but we also added a pressure regulating tank as well, just to make sure we have very consistent pressure during our tests. This is just showing some of the materials we've tested so far. So this is copper, type L. We have different types of elbows that we're testing. So we have what we're calling a short radius sweep and a long radius sweep. We also have something called a swoop, and just longer radius is the difference between those. For PEX, there's a lot of variation materials that you can get. So this is just showing some of the different materials and like technologies of how they connect. Some are push to connect, some fit on the outside, some seal on the outside, some seal on the inside, some crimp. And there's also bend supports too, where you're bending the PEX pipe. And as you can see, we got some internal pictures here, but the insides vary a lot too, the inside diameter. So, you know, how does that affect the pressure drop that we're seeing? And then we're also testing couplings and tees. This is the same technologies for the PEX here. And in general, our methodology, we have more on this, but this is just to preface so we have the test segment that I showed before. So we test one of those, and then we test an equivalent straight pipe of the same length. And then basically, you know, subtract the 2 to get pressure drop per fitting. And then we also are calculating the equivalent length per fitting as well. So now jumping into the results. So far, we've tested about 50 combinations of different fittings. And we've tested 1 inch and 3 inch so far, but we are, like I said, this is still ongoing and we're testing more. So this is 1/2 inch copper. On the left here, this is the scale blown up a little bit. On the right, that's the scale of the PEX pressure drop. So you'll see that in the next few slides. But showing here, so at 1/2 inch copper, the flow rate at the velocity of 4 feet per second, the flow rate is about 2.9 gallons per minute. So just point out that number. So at 4 feet per second on our graph here, what we were testing it at, the pressure drop is about 0.05 PSI per fitting. And then going into CPVC, which we also tested, looking again at 4 feet per second, that corresponds to 2.3 gallons per minute. Looking at that, the pressure drop is about 0.13 PSI per fitting. Now going into PEX. So on the left graph here, we have tees and couplings, and on the right, we have elbows. So looking again at 4 feet per second, that corresponds to 2.2 gallons per minute. Looking at that on the graphs with elbows on that graph to the right, from 0 to 2.5 PSI per fitting. And there is a very large range in what we've been seeing as well. And if you look closely, that line at the bottom is the bend support. And yeah. So this is kind of us comparing the bend support and our different variations in what we're considering straight pipe. So the colors represent, there's straight, and then there's one called curved, which is just one long curve. And then the coil is a tighter coil around that test segment that I showed earlier. And then the bend support is using 10 of those bend supports to coil it around. And as you can see, they're all pretty similar in their pressure drop. So again, at 4 feet per second, the pressure drop is about 0.1 psi per foot. So that bend support, it's making multiple 90-degree turns. And yeah, so that's just interesting to see. And now we're going into 1/8 inch. So this is for copper. Again, so looking at the velocity 6 feet per second, that corresponds to a flow rate of 2.7 gallons per minute. So now looking at our graph, looking at that 6 feet per second, it ranges from 0.1 to 0.3 psi per fitting. And now going on to PEX, again, we have T's and couplings to the left, and now we have elbows to the right. And looking at 6 feet per second, it ranges from 0 to 4 psi per fitting. So I'm also going to show we also tested some shower valves as well. I think we tested about 10 of them. Yeah. And this is just seeing some context here. So what does the pressure look like at a second floor shower? So shower heads are rated at 80 psi. So you go up 20 feet, you go through a shower valve, and you have some losses in the piping. So the residual pressure could be about half that original pressure. And that corresponds to about 70% of that original flow rate. So where did all the pressure go? Yeah, so these are our shower results. So just pointing out on the graph here, from about 1.25 to 2.5 gallons per minute, which is like typical shower flow rates, the pressure drop roughly doubles from lowest to highest. Yeah, and up to like 25 psi. So we also looked at the tub valve as well. So above 2.5 GPM, there is also a range, like a doubling that is happening. So between 2.5 and like the highest flow rate around 4. There's a wide range, and it goes up to around like 50 to 40 psi, and some are a little lower. Yeah, but just a note here, actual flow depends on the available pressure. So in summary, there's more testing to go. We haven't published any of our numbers yet, but we welcome questions. We're happy to help with any like specific project questions. And yeah, we have more testing to go, like I said, and bigger picture, it matters, pressure drop matters if we want to right size plumbing systems. And with that, I thank you, and we're right on time. So thanks, y'all.
You did great, Emily. Thank you very much. So I don't see any Q&A from the audience at the moment, and I think we should move forward. So Rich Poole, I think you're up next.
All right. So as Emily touched on about right-sizing plumbing, we're going to get into that a little bit at this point in time. We are just going to scratch the surface of this topic as we don't have a ton of time, and we could chat about this for hours, as Gary and I have done. But we're going to talk about a little bit about the evolution of plumbing, what our current sizing methods are, a little bit about sizing with the calculator from iAtmos Appendix M out of the UPC, and then talk a little bit about taking that a step further to sizing based on actual fixture flow rates That impacts basically your branch lines. And then we're going to talk about the impacts of oversizing plumbing systems on water quality, just very briefly, and what's going on today. So if we take a look at what's happened in the last 20, 30, 40 years, we're in an age of water conservation. We hear people chat about conserving our natural resources, which is a very good thing. And so we have seen since the 1994 federal requirements a significant reduction in flow rates. You know, I'm sure you've all heard about the WaterSense program and are very well aware of it, but that's pretty much become widely accepted throughout the U.S., and it continues to drive fixture flow rates even lower. We also have some jurisdictions that have taken it a step further. So if we take a look at the chart at the bottom of the slide, you can see where currently we are with fixture flow rates, the WaterSense flow rates, you know, what the lowest numbers are in the U.S., and compared those to the pre-1994 federal regulations, you'll see a significant reduction in what our flow rates are today. When we look at the impacts on sizing, you know, our system sizing in the UPC, short of Appendix M, the IPC, they date back 70 plus years. And we've seen a drastic reduction in fixture flow rate as well as how houses are designed or buildings are designed today. You know, the code plumbing sizing is based on Hunter's curve, which was developed in the 1940s. And if you think back to the 1940s, not a lot of us were around. There's a few of us, but not a lot of us were around. But a typical 4-bedroom home back in the 1940s had one bath, maybe two if you were really, really lucky. Today, there's typically at least a 1-to-1 ratio of bathrooms to bedrooms. In addition to that, if you looked at a hotel back in the 40s, a lot of them had communal bathrooms. Well, today, every hotel room has a bathroom in it. So if we look on demand of our fixtures, it's significantly different today than it was back in the 40s when our sizing was established. You know, when we couple the antiquated plumbing sizing with reduced fixture flow rates, it's had a significant impact on our system performance. Our systems today are significantly oversized. So if we take a look at our current code sizing, and this is a methodology out of the Uniform Plumbing Code using Chapter 6. If we look at a typical 3.5 bath home as a basis for our design, we add up all of our fixture supply or water supply fixture units for all of our fixtures. With that, we come up with a total fixture load of 41 water supply fixture units, 21 for hot, and 33 for cold, which is based on taking 75% of the total value for hot and cold when you have a fixture that uses both hot and cold water. When we use those fixed water supply fixture units, we're going to assume, for purposes of our example, that we have 60 psi at our inlet and a total developed length of 150 feet. And when we use the table 610.4 of the Uniform Plumbing Code, what that leads us to is a 1.25 inch water service line. And then the cold water reduces down to 1 inch after we split off to the hot water tank. And then the hot water line, the main trunk line, is going to be a 1 inch line as well. And then if we take that, Appendix M was developed, and the sizing calculator was developed on the premise of what we're talking about today, that our systems are oversized. And if we use that same mentality using the calculator, what we see is our water service line demand is 11 gallons per minute, and we'll get into a chart that compares these two in a second. Our cold water demand is 8.3 GPM, and our hot water demand is 8.3 GPM. And if we look at a velocity regime between 5 and 8 feet per second for various pipe material, we can result in the following pipe sizes, which for our main service line would be a reduction down to 1 inch, a cold water trunk line at 3/4 inch, and the hot water trunk line at 3/4 inch. I have this slide before because I want to talk about this a little bit. If we use actual fixture flow rates to size our branch lines to each of the fixtures, similar to the UPC Appendix M, we can change how we size those fixtures. So instead of applying a water supply fixture unit to a lab, we can actually use the flow rate of that fixture. For example, if we have a 2.2 gallon per minute shower, instead of using a water supply fixture unit and what the UPC tells us we need to use a 1/2 inch line, we can actually reduce the pipe size to deliver the amount of water we need at those fixtures in keeping our velocities within the flow regime where we're in the transitional to turbulent flow range for scrubbing effects on the pipe. More research is needed to be done to evaluate the accuracy of the assumption. There have been some studies that have demonstrated that Appendix M in the calculator is still overly conservative. But as Emily mentioned, more work needs to be done to determine, our pressure losses to make sure we have adequate residual pressure at our fixtures to properly size the system. A short-term solution in today's world is to use Appendix M to size your trunk lines and then size your branch lines based on the actual fixture flow rates. This is a good compromise now until basically all the research is completed and we look at our plumbing sizing methodologies holistically and come up with the best approach. Here's a comparison of using Appendix M of the UPC, the calculator, versus Section 610 of the UPC. And as you can see, the calculations for flow rate of our lines are significantly different. For the water service line, the current sizing methodologies of Section 610 require us to deliver 25 gallons per minute, whereas the water service line coming out of Appendix M is 11 gallons per minute, so less than half of what we are currently required to install according to the code. This obviously has a significant impact on your system layout design in sizing. Oops, wrong button. But if you look at why is all this being done, I'm sure you all have heard the statement bigger is always better. But unfortunately, that doesn't apply to our plumbing systems. A lesson that is being realized today. Oversizing plumbing systems have had an adverse impact on water age, scrubbing effects of the pipe walls due to very low velocity in that laminar flow range, and then hot water delivery time. The more water we have sitting in our hot water lines, the longer it's going to take to get to the fixture. All of these impacts have culminated in a ton of discussions today concerning our water quality, biofilm growth, and overall system or water quality of our entire plumbing system. It's getting a lot of attention today. The National Institute of Standards and Testing, NIST, they're focusing on it, as well as so many other different people are focusing on our plumbing system. This is one major topic that is the center of that, and that is our system design. In conclusion, the only constant in our plumbing systems over the last 70 years has been our sizing methodology. That's the one thing that's never changed. Water temperatures have changed, fixture flow rates have changed, the type of fixtures we use have changed. as well as the number of fixtures and usage patterns have completely changed. It's time for our plumbing sizing to catch up to today's advanced plumbing systems. And that concludes my presentation. It looks like we do have a question. No, okay, that was from previous.
You do have a question. Rich,
what is that question?
Rich, that was wonderful. And the question is from Jim Lutz. Rich, have you looked at what elbows and fittings would do to the overall sizing calculations?
Yeah, and that's part of the next step to designing the plumbing system, as far as determining what our pressure loss through the system. That's going to have an impact on obviously how we size our systems. It may change what available pressure we need to have. So it may change the incoming pressure requirements, PRV settings. But yes, when we get into the overall system design, as Emily had indicated, when we look at right sizing our plumbing systems, pressure loss becomes a much, much bigger topic of discussion. Right now, there is so much oversizing in our plumbing system that pressure loss really is irrelevant to our design. But as we get skinnier plumbing systems, pressure loss becomes more of a real factor. So when we design our plumbing systems moving forward, we need to design those plumbing codes based on actual pressure losses, which ties into the work that Emily and Gary are doing.
Thank you, Rich. One of the things that we found in our research is that the pressure drop per fitting actually goes down as fitting sizes get bigger, particularly for insert fittings. It's true for all of them, but the particular interest is the insert fittings. And because they're sort of the same wall thickness of a fitting, but the diameter of the pipe is twice as big, so it takes up less of the middle. And so that's not what all the handbooks talk about right now. The pressure drop per fitting gets bigger as you go up in size, and that's just not what we're measuring at all in the lab. So there's still some interesting confusion that needs to be sorted out, which is why you and I have this conversation all the time about what needs to get measured next.
Exactly.
So all good. With that, I think we should move on. Our next speaker is from NREL, and why don't you take it away? Go ahead, Jeff. It's all yours.
Hi there. This is Jeff McGuire from NREL. This talk's going to be a little bit different than the previous ones. What I want to talk about today is a lot more simulation-based. And when we do simulations of water heaters, how we quantify the unmet loads and how we determine what level of unmet loads might be acceptable. So a little background on just simulation models, because this is a little bit of a different topic for the session. Water heater models are used in a lot of different ways. If you do a home energy rating, you get a Hertz index calculated for your house. There was a model of the water heater in there. If you're trying to comply with any performance-based codes, then the water heater would be simulated for that. The use case that I'm most involved in is predicting energy savings and cost effectiveness of upgrades. So if you switch from water heater X to water heater Y, how much energy do you save? Is it a cost-effective thing to do? And so you can use simulations to answer those sort of what-if questions. Most of the models out there today are either a mixed tank or a stratified tank. So mixed tanks would assume that the entire tank is isothermal at one temperature. It's used in a couple situations, but a stratified tank generally provides much more accuracy. So when you model a stratified tank, you have a whole bunch of isothermal nodes distributed vertically to capture any sort of stratification in the tank and the differences in tank temperature. So when we do these simulations, we do get water heater energy consumption and the delivered energy and the outlet temperature, but there isn't really a good standard metric for unmet water heater load in residential simulations that I've seen. So I want to spend some time today talking about when I do these simulations, what my thought process has been when I try to quantify unmet loads, and hopefully see if that makes sense to everyone here, get some feedback, and kind of try to start the discussion about how to do this. So for example purposes, I ran simulations of an electric resistance and a heat pump water heater. They were installed in the basement of a home in the Denver metro area. And we did annual simulations in Energy Plus with a relatively high hot water use. So this was about 80 gallons per day were simulated. For the heat pump water heater, there was some backup element usage to make sure that you were meeting the loads. And so if you look at the consumed and delivered energy consumption, the heat pump water heater saves energy, which is expected and great. It also delivered a little bit less energy. And so really the question is, would this be acceptable for a real occupant? Would they be okay with that? So there's an example here of one particular day where there happens to be a lot of draws in the early afternoon. And so the outlet temperature of the heat pump water heater drops a bit more than of the electric resistance water heater. And so the question is really, is that okay? Or is that something that would be a problem for the occupant? And how do we quantify that in simulation and make sure that when we're recommending an upgrade, we don't recommend something that's going to not be acceptable? A little bit more about hot water use in simulation. So when we do simulate hot water use, we generally do consider the end use. So the 5 major end uses would be showers, sinks, baths, clothes washers, and dishwashers. And so we specify an end use to allow for better capture of water saving measures. So if you install low flow shower heads, then you only affect the shower draws. Generally, we don't specify it all the way down to the fixture level. So what I mean is that we specify, yes, this is a sink draw, but we don't say it's the master bath sink or sink 2 or the kitchen sink. And a problem with that is that a lot of these simulations don't include an explicit distribution system model. And so obviously there are some losses in the distribution system pipe that affect your outlet temperature. And so that's generally neglected in a lot of simulation models right now. In some cases, they might have some heat gain associated with hot water use and the distribution losses, and possibly some additional water use to account for any sort of losses in the distribution system. But it's generally not an explicit model of all the pipes in the house. And when we talk about hot water draws and we have these end uses, so we can use field data, we can use sort of standard data for what the draw is out of the water heater, or we can generate synthetic draw profiles, which I think is what a lot of tools use. So generally the synthetic data would be something that's generated from a whole bunch of field data. At NREL, we have a tool that generates hot water draws for these 5 end uses that we frequently use based on a whole bunch of field data. And so we have that tool so that we can generate additional draw profiles beyond what we've seen in the field. Okay, so in terms of an unmet load metric, the goal is really to make sure that the occupants are comfortable. So to make sure that they're getting enough hot water and that they feel comfortable and happy with their new water heater. So when we talk about the different end uses, not all of them are felt directly by the user. Showers is the most obvious one, where you notice if a shower is not hot enough immediately. That's usually what people would complain about. So any sort of discomfort there is something that's immediately noticeable for the user. For sinks, a lot of the time you don't even wait for hot water to get from the water heater all the way to the end use. A lot of sink draws are only a few seconds. Hopefully these days everyone's taking at least a minute to wash their hands. But in a lot of the data, there's really short draws for sinks. So if people aren't even waiting for hot water, should we count that as being discomfort if the water coming out of the water heater isn't hot enough? For baths, that's something where you do definitely feel the water temperature, but a lot of bath draws are really sort of energy draws, where what really matters is the final temperature of the bath. So if you want your bath to be at 110 and you start drawing at 115 and the temperature sags during the draw and it gets down to 90 right at the very end, if your bath is still the temperature you want, that's probably fine. That's generally would be acceptable to the user based on how you actually use hot water. Dishwashers and clothes washers, they're not felt by the occupants, so there isn't really any discomfort associated with not providing hot enough water. Dishwashers often have a booster heater that heats up the water anyways. In our simulation approach, we do account for that and simulate the booster heater. So that's another way that we quantify if you're not providing enough hot water, it ends up in the booster heater. So how hot is hot enough for a shower? It depends on the person. Everyone has their own preferences. We do need a standard temperature if we're going to quantify unmet loads in a general way that can be applied to every situation. Typical shower temperatures range from anywhere between 105 and 110, and it depends a lot on the person. There is a standard out there, the Building America House Simulation Protocols, about ways to model residential buildings. And they do have a specification in there of 110 degrees Fahrenheit. So that would be my suggestion, is to calculate unmet loads whenever your outlet water temperature is below 110 and is going to a shower. Being on the higher end means that you're accounting for everyone's user comfort preferences. If you prefer 105, that's great. You're still comfortable. And being on the higher end also is an attempt to allow for a little bit of distribution losses of a degree or two and still being pretty close to comfortable without explicitly modeling the entire distribution system. So in terms of quantifying unmet showers, let's say that our goal is to have some metric related to any time you have a shower draw and your outlet temperature at the water heater is below 110, and you think that's going to cause discomfort. So you could look at the time that you have water draws where you're not at that comfortable temperature. But if you just look at time, that doesn't track how low your outlet temperature got. There's a difference between getting 109 degree water and 180 degree water. So any metric, you kind of want to account for that. If you track temperature, then you miss the time portion. So really what I think is the best way to do it is to calculate the unmet shower energy. And so that's basically calculating the area under that curve. And it's basically the MC sub P delta T between the temperature you're actually getting and the temperature that it would be comfortable. So it's pretty similar to having some sort of imaginary electric resistant heater that just heats it up at a COP of 1 right up to the comfortable temperature. And so that's my proposed metric, would be to calculate the unmet shower energy when we're doing annual simulations. The problem is how exactly to use it. So let's say I calculate that this home has 3 kilowatt hours of unmet showers, and if I change it, it's going to go to 5 kilowatt hours of unmet showers. It's hard to tie that back to exactly, is this, is the occupant okay with 3 or 5, or how much are they really comfortable with? Because there probably is a little bit of hot water run out, and that's especially true in simulation. Where we have draw profiles that might say that you shower for 10 minutes. In reality, if an occupant starts feeling that the hot water is getting cooler, they might try to wrap up their shower quicker and end it a little early, maybe 8 or 9 minutes, to avoid that discomfort, or they might shower later. Those sorts of behavioral changes are really hard to capture in simulation with specified draw profiles. So if we want to come up with some sort of criteria for what's acceptable, one possibility would be to look at field studies. If we have measured data for the outlet temperatures of the shower, and we have data on occupants to say if they were comfortable or not, that would tell us what the minimum is that's acceptable, but it wouldn't tell us where the threshold is. So it wouldn't tell us when we cross that line. So one option that I've been looking at is running a baseline simulation of what we consider to be acceptable situation. So where you have an electric water heater and it's sized correctly, and look at how many unmet showers come out in simulation and use that as the criteria for determining how much is allowable, making sure that you provide as much as what we think is a reasonable baseline with the same draw profile. So this is just an example of that. I ran it at different climate zones, different mains water temperatures. So you can see even just depending on where you are, there's some difference in this metric. Okay, so this is a metric I came up with based on some discussions with other people. If there's anywhere I'd like to get feedback from, it's this audience in particular, and see what people think, see if this is a good idea, see if they think just focusing mostly on the showers is acceptable. Should we include other end uses? If so, how do we distinguish between the ones where they wait for hot water or not? We're neglecting distribution systems. Do we have to fully model an explicit distribution system to be able to capture this accurately? Or can we do something else? And then the acceptance criteria is a really hard one too. How do you determine what's actually acceptable? And making sure that you're not predicting this energy savings, but you're doing it in a way that'll make the occupants unhappy. Because you don't really want to be predicting something if it's not actually going to satisfy the occupants' needs. And so that is, that's all the slides I had. I hope people found this interesting, and I do really hope people will come to the chat and talk about this and let me know what your thoughts are.
Thank you very much, Jeff. Great presentation. You raised lots of good questions. We did have a Q&A from the audience, actually a couple of them. This is from Brennan Mangino, I think. During your example simulation, what volume, heat pump capacity, and electric resistant element size did you use?
So it was a 50-gallon heat pump water heater. The element was 4.5 kW, and the heat pump size, I think the nominal was around 970 watts as output. It's based on a real manufacturer's equipment. It's a model that we developed based on lab data from a product that's actually out there.
Okay, you have another question from Rick Mayo. Can I request the additional stratification data you have on the vertical tank style water heater?
Sure.
If you say yes, I'll connect you.
Okay. Yeah, we can talk about that. We do simulations of stratified tanks. We don't always capture every single tank temperature in every simulation, but I do know that we have some of that data available. And I'm sure we can work something out.
Rick, if you can come to the chat room for a little bit, you'll be able to focus in on a better set of answers. And we have another question from Peter Skinner. Have you worked on multifamily energy input and storage optimizations?
I have not done a lot of work on multifamily yet. We have some upcoming projects that are really going to be focused on multifamily water heating, looking at heat pumps in multifamily, and I'm sure be doing a lot of simulations of that. So not yet, but I'm going to soon.
Good. And then another one from Jim Lutz. Do we need an explicit distribution system model? His answer is yes, with an exclamation point, maybe downgraded for building energy simulations. I suspect Jim's going to try and join us during the chat room. All right, enough of those for now. I have several, but those will wait till the chat room. And I'd like to continue on with Yanda Zhang. Yanda, are you ready?
I'm ready, Gary.
All right, you hit the slide button where you want to start, and it'll go.
Okay, hi everyone.
Thank
My
you.
name's Yanda Zhang. Yeah, thank you, Gary. So I'll be presenting a study on distribution systems for single-family homes. It might answer some of the questions that Jeff discussed in his presentation, but the focus is mostly on efficiency. And the study is funded by the California Energy Commission. The RICH team include Gary Klein, Jim Lutz, John Kohler, and myself. Yeah, if you have any problem with the research, talk to Gary. So the study goal is to develop code change recommendations that can improve the system performance significantly. So the key is to find strategies to make significant improvement. The second goal is to characterize the impact of low flow fixtures on distribution performance. And there was a goal to assess access the lowest flow possible. But that goal was later removed based on recommendations by our technical advisor committee. So for the study, we systematically considered the improvement strategies, include some of the very aggressive ones. Our starting point is a system with streamlined pipe design. So the baseline is a reasonably well-designed system. And then we consider the 4 groups of improvement shown by those 4 green boxes in the middle. So for pipe layout method, we have 5 options, including one of the aggressive method is to use 2 water heaters. And then for water heater locations, you can see on the right side, there are 5 options. There's also an aggressive improvement approach is to number 4, to move water heater to the center of the wet room rectangle. Basically, is to move the water heater to the middle of the house to be close to fixtures. And then for fixture location / architecture design, we have 2 options. One is a normal architecture design. You have fixtures scattered in the house. And the second option, you have a architecture design allows a compact core, means fixtures will be close to each other. And then for pipe sizing, you can see we consider 3 options. One is to reduce 1/2-inch pipe to 3/8. And then for the 1-inch pipe, we reduce them to 3/4 inch, right? In Jeff's early discussion, he discussed it's possible, right? You can use UPC Appendix M method to do that. And then we consider the option by reducing both small pipes and large pipes. And then towards the end, we consider the impact of low flow fixtures. And we considered by reducing shower flow from 1.8 GPM, which is the current California standard, to 1.5 GPM, and reducing bathroom faucet from 1.2 to 0.5 GPM. So this diagram shows you what the distribute core versus the compact core will look like. And the blue rectangle indicate what we call wet room rectangle, which is the rectangle that can just cover all the fixtures. That's the way we can use, right, to clearly indicate kind of how compact fixtures are located. Now here we give an overview of what the different options will have, right, for the pipe layouts and fixture and water heater locations. And please note, when you have a compact core on the right side, fixtures are located close to each other. We don't need to have an option to have 2 water heaters. Now, so for performance model, we developed a new modeling method that consider the transient delivery process of individual draw events. And the model is based on lab testing data. And the model, in addition to provide the delivery time, but also provide the detailed energy implications in terms of how much energy is used to fill the pipe and how much energy is lost to the ambient through heat loss, and then how much energy is actually delivered. For example, the diagram here, the green area shows how much energy is actually delivered to the fixture. Now, we also have a model allows to quickly configure distribution configuration, and so they can look at a very broad range of distribution designs. And we use the Title 24 draw schedule to come up with detailed draw events. So with that model, we can obtain performance, detailed performance. You can see for individual fixtures, from the top, the fixture, we have MBSH, that stands for mass spectrum shower, and then you can have mass spectrum sink 1, and then sink 2, so on, right? So we also can look at the different energy component during the delivery process. You know, if you look at the second column, the title says energy supply by the water heater to the fixture, for the fixture, not to. And then the third column shows energy delivered to the fixture and used. And then we have energy delivered but wasted. And then we have two energy components that's showing how the energy is dissipated into the ambient. And then those data allows us to calculate the overall distribution efficiency for individual fixtures. And then you look at the last column, we can have the overall distribution efficiency. In this case, for the baseline, it's 60%. But you can see that variation is very large among different fixture type. And also, it kind of definitely depends on your draw schedule. Now, we also perform the same, right? You can obtain the same performance in terms of water use, and then we also have the similar performance in terms of delivery time characteristics for different fixtures. And then we also have what we call performance in terms of service. This is the kind of where we also address the load not met issues. Not going to the details. You can maybe look at the data later on. So now, with all that explanation, let's look at the final performance impact. You know, first, let's look at a system where have distributed core fixtures are not concentrated, scattered, and with normal pipe size, basically no small pipes, and normal flows. So focus on the last column. Last column shows distribution energy loss reduction. This is compared to the baseline percentage reduction. Again, reminds you the goal is to find significant reductions, right? So now, which other ones give you significant reduction? You can see towards the bottom, there's 54%, 64% reduction, right? Pretty impressive. Both of them are associated with using 2 water heaters. Yeah. And
time check, 5 minutes.
Yeah. Go to the next. Thanks, Gary. Go to the next one. If we see how using small pipe is going to affect the performance, and again we can see that using 2 water heaters give you a significant reduction. Also, the central manifold system using 3/8 pipe also give you pretty good distribution loss reduction. So now let's look at the system with compact core. That means fixtures are close to each other. So what do we find is that the distribution loss is reduced only when the water heater is also moved close to fixtures. So having fixture located to each other itself is not enough. You also have to bring the water heater close to fixtures. So now let's put all the improvement strategy together to see what would be the overall improvement we can achieve. And again, look, if you focus on the last column, you can see many rows has large percentage reductions, right? So, but if you look closely again, they are all associated with having water heaters close to the fixture, right? So now let's look at the impact of low flow fixtures. And this time, let's focus on first the blue columns that shows you the distribution energy loss, right? The comparison between you have low flow versus normal flow. What we find is that low flow increased the distribution energy loss, but by a very, very small amount, right? So, and on the other side, low flow fixture definitely reduce the overall energy use. I'll show it on the right two columns, kind of the green, two green columns, about 12% overall energy reduction. So let's just start the question, how low can we go? And so we identify the ones that really give us a very high energy use reduction. And most of them, if you can see, are associated with, look at the first column, associated with compact architecture design, means fixtures need to be close to each other. And also for them, we also have to have the water heater close to the fixture. So moving from the garage to be somewhere within the house or somewhere close to the fixture. Only one option that is using distributed core that requires 2 water heaters. The overall energy reduction is 26%, significant, but that happens when you also use low flow fixtures. So based on that, we provide some recommendations regarding Title 24 building standard improvement. For example, recommending not using winch pipe, provide compliance credit to have compact wet room size, and discourage the use of long, large diameter one zone pipe layout. For Title 24, we recommend that, to explore the requirement of for single handle faucet with a cold start function. I haven't discussed details of that. This is basically to eliminate unintended hot water use. Those use actually never had actual hot water delivered. So find a ways to eliminate them. I think towards the end, we also find that, the traditional improvement strategy have limited improvement potential. The ones with aggressive improvement strategies, they do face large market barriers, right? For example, you have having compact architecture design, moving the water heater very close to the fixtures. From design point, it's hard to achieve. I think we recommend think that innovations needed in terms of system design, component, and control method that bring water heater sources to be very close to fixtures. That is the future we should consider to significantly reduce distribution loss. With that concludes my presentation.
Thank you, Yanda. We have a few minutes left for this discussion here today. Any of the people on our panel today have questions for anybody else on the panel at the moment? And those of you who are on our panel could come back so I can see you. And so could the audience. Oh, someone's got a loud background mic. All right, Yanda, I had one question for you while we're waiting to see if anybody else does. What would have happened to the master bath shower efficiency if it was the first use in the bathroom instead of after the sinks?
Well, certainly it'll be reduced. That's a very detailed observation, Gary. Here we're showing the master bedroom first row has a very high efficiency. The reason is because for this drawer schedule, there are prior drawers from the master bedroom sink to prime the pipe. So that by the time the shower is taken, the main trunk is already warmed up. That's why you have high efficiency. So that's what we say, the overall efficiency or efficiency for individual fixture definitely depends strongly on drawer schedule.
Yeah, I think that's relevant to the work that Jeff is doing for characterizing unmet loads and for any of us who are trying to model hot water use. What we did, I thought that was very interesting, Yanda, that you came up with an idea of how to look at it. was that we would characterize separately the actual need for hot water, not what got delivered first, but how much energy is needed by the consumer at the shower, at the sink, assuming they got hot water. And for our purposes, we had a magic system that did that because there are no distribution systems that are as good as that. And so with that in mind, that this technique of separating it into the various parts turns out to, I think, have been a very useful research tool. Okay, my background got loud. We have a dog in the background. New. All right, so I think we need to effectively conclude this session and move to the chat window. I do see a question from Matt Malinowski. I'll answer that. In South Africa, water heaters are often installed in the attic. This could promote a more compact design. Any examples of this in California? I will answer that it's rare to see those in California, but it's not rare to see that in Houston. And Jonah Shine, can we see the dog? During the video chat, Jonah, during the video chat, he'll come see us. With that, I'd like to conclude. Thank you to our speakers for their presentations and for the attendees to participating in today's webcast. Again, if you would like to continue exploring these topics more with the presenters, please follow us to the Zoom chat room. Thank you for attending and enjoy the rest of the day. Bye-bye now.
Bye.
Yeah. All right. I'm going to log off, I think. We're good. I'll see you all on Zoom. Bye, everybody.